all the way to modern times, when is now known to about 11 pp with about 11 part per million uncertainty. Having said this, though, you can see on the sketch to the or on the plot to the right, the various measurements of big G in the last, not since 17 whatever, but in more recent times, and you can see that they are kind of all over the place. There's clearly systematics that are not well understood because the uncertainties that are quoted are quite a bit smaller than the dispersion between the various measurements. So clearly there's some systematics that we don't understand. But just to give you an idea, even if you ignore those systematics, that's known to 11 ppm, and the alpha of electromagnetism is known to a quarter of a ppb, and even the weak coupling constant is known to half ppm. So gravity, this is just to say that the strength of gravity is not particularly well known or understood. Now, however, and so you may say, well, okay, so then we should just be measuring G and big G. And now there are plenty of people doing this. In fact, the NSF recently had a call for proposals to actually for people with new ideas on how to measure G, just because there are those kind of discrepancies and anomalies. However, there's no, unfortunately, physics, theoretical physics doesn't know how to predict big G. And so it's not clear whether, finding one value or the other, doesn't tell you anything about, how good the underlying theory is. And so for that reason, the thing that, in my opinion, at least, is more interesting is to actually measure how well the inverse square law works at all distances. The inverse square law of gravity, because that's actually where you would actually discover problems, if there are some problems in the theory. So that's actually, so we should talk a little bit more about this. Gravity is not part of the standard model of fundamental particles interactions. And that's just simply because we don't understand how, people smarter than me haven't been able to actually incorporate it in the standard model. At the same time, we have this quite ambitious idea that essentially gravity will behave like Newton's law of gravity all the way down to length scale, to the Planck scale, which is essentially a distance of 10 to the minus 35 meters. And this bold assumption that is in part, is the assumption that from which you start when you say that we don't know how to incorporate gravity in the standard model. That kind of assumption doesn't have essentially experimental verification at distances much smaller than a meter, or maybe than a millimeter, let's put it this way. So there's many, many orders of magnitude where we're flying blind, and no wonder we cannot really make sense of gravity much. So this is really very important. It's a very, very important topic in experimental physics to actually check that. Now, of course, there's no way we can measure this at 10 to the minus 35 meters, but improving things a little bit is a really good start. Although this is not necessarily always the case, but the way I'll be parameterizing deviations from the inverse square law is to actually use a Yukawa potential, and so write the potential as is written here, with Newton's constant times the two masses over r times 1 plus the correction that has a strength, that is alpha, and then has a Yukawa exponential behavior with a cutoff at a scale called lambda. And this is what we know empirically. This spans very many orders of magnitude. You can see from 10 to the minus 2 meters. And in fact, I will show you later plots which are actually detailed down here, well, even below 10 to the minus 2 meters. But this plot particularly goes from from centimeter scale all the way to 100 astronomical units. You can see that, in fact, I have at the bottom, at top, the scale is in meters, at the bottom is in astronomical units. So it's convenient. And I always like to show this plot because there's lots of physics contained into this. Now, the vertical scale, so the horizontal scale is lambda from Yukawa correction, or the lack of a Yukawa correction, and alpha is the strength of such a Yukawa correction. And so the gray part is the part that we have excluded from experiments. So we know that the alpha is smaller than is whatever you read here for different length scale lambda. Let's see, just for fun, the place where we know gravity the best is at the distance of the moon, between the Earth and the moon, because we've done lunar ranging, laser lunar ranging for now many years. And essentially we have mapped the orbit of the moon to within a centimeter, with uncertainty of centimeter, which is really impressive. And so by studying how well, by studying the orbit of the moon, you can tell something, say something about deviations from the inverse square law at the scale of the radius of the orbit of the moon. As you go to larger and larger distances, you actually get into the problem that, so you can see there are here some dips that have to do with the diameter of the orbits of various planets on the solar system, except when you get very large orbits, the orbit takes too long, and we haven't had enough time as a human species to actually investigate that orbit precisely enough. Long time ago, now 20, 30 years ago, there was the Pioneer spacecrafts reported some sort of anomaly in their acceleration. It turns out that was an instrumental effect. A few years ago, we actually proposed a new spacecraft type to actually do this measurement better. But again, that's another one of those projects that is very large. And I was telling Yuri earlier, I don't have time to do more than one big project simultaneously. So that's sort of a kind of a wish, but there's no real action as far as I know on this side of this plot. And then as you go down to smaller distances, you see that there is this regime which has artificial satellites. There's actually investigations done by putting satellites in orbit and essentially studying their orbits. If the satellite becomes too low, now there are corrections from atmospheric effects. And so the measurement becomes less and less sort of powerful, if you want. And then there is this intermediate region here where the scale is of the order of 1 kilometer or maybe 100 meters, where essentially measuring the inverse square law of gravity is a degenerate process with measuring whether there is a uranium mine or an iron mine or something. In other words, the non-uniformity of the Earth's crust and mantle dominate the scene, and so the measurements are not particularly good. And then there are lab measurements, which is what is today's focus. So we'll be focusing on the far left of that plot at very short distance. Again, in the way of justifying this, one can take the point of view, which is actually my favorite, that essentially gravity is such an important thing that you should measure it no matter what. It doesn't really matter whether there's any theoretical prejudice or something. You need to measure gravity because it's a really important thing. But in addition, there are theoretical reasons to actually suspect that maybe there is a deviation from the inverse square law. I guess the main point of view, or the main thing that people wonder, is why gravity is so much weaker than other interactions. And at the same time, that is not well incorporated in quantum mechanics, if you want. Maybe those two things are related. Maybe they're even connected with dark matter or dark energy. But one, to just give you an idea, one possible explanation has to do with extra dimensions, where you say, well, there are many theories sort of predict or somehow expect there to be more than 3 spatial dimensions. Now, of course, at macroscopic level, we know that there's no more than 3 spatial dimensions. So generally, this is explained by saying, well, maybe the extra dimensions are, as I call them, compactified or essentially curled up at a scale that is called A here, so that when you are larger than A, everything behaves like there's 3 dimensions, but then when you go below A, there's more dimensions. And as you know, Gauss's theorem relies on there being 3 dimensions, so that if you have, when you go to shorter scale, and you essentially have to account for those extra dimensions, things may behave quite differently. And one possibility is that gravity essentially that all the other interactions, in particular E&M, lives on the 3 dimensions, essentially on this kind of sheet. This is a 2-dimensional interpretation of our world that is 3-dimensional, but so E&M always lives on this kind of sheet, whereas gravity goes across the bulk. And so the scaling of gravity is different from that of E&M, and in particular, it's not, it violates 1/r². This is one possible way of doing this. Other ways are maybe there's other interactions that maybe depend on things like baryon number or other properties of matter. And at short distance, maybe those things, those interactions become important, and they look like a modification of Newtonian gravity. Again, the reason is a little bit different now, but the effect is the same. Essentially, they give you an effective behavior that is not 1/r². Okay, so from the experimental point of view, now we're switching to experiment. The challenge is twofold. First of all, the density of the objects you can use to measure gravity is whatever it is. If you're very aggressive, you use, I don't know, platinum, which has density about 20 grams per cubic centimeter. But that's it. You can't use a higher density matter. Neutron stars cannot be used for this, and so you're stuck with that. That means that as the volume of the objects becomes smaller and smaller, since density is constant, you end up with a force that scales with the 2 volumes multiplied together. This is r⁶ divided by r², and so the force scales with r⁴ power. So as things become smaller, the force becomes smaller very, very rapidly. And so that's a problem now. So if you're testing things at 10 micron distance, the force from between 2 spheres is about 10 to the minus 21 newtons. So those are really very small sort of forces. Now, in addition, so this means that the measurement has to be very sensitive. In addition, there are tremendous backgrounds, because when you go, say, below 100 micron distance, there's always electromagnetic interactions. Even between neutral objects, there are multiple moments. First of all, dipole moments, but then higher order moments that essentially are either they're permanent, that is, they come with your objects, or they're induced, and that means that you always get some fringe electromagnetic interaction that essentially is a background to the measurement. And we'll see plenty of those later in the talk. Traditionally, those measurements have been done with Cavendish type torsion balances. And you see here to the left, the one from the University of Washington, that is essentially the group that does, historically has done the best measurements in this case. And those are really superbly designed torsion balances, but they are also macroscopic objects. You see, the size of this thing is about that of a Coca-Cola can. And sometimes if you want to go to really short distances, there's all sorts of artificial problems that come from the fact that you need to machine your Coca-Cola cans so that things are parallel to within a few microns and all this kind of stuff. So the idea is that it would be nice to do something which is intrinsically miniaturized, essentially. In addition, those kind of experiments that I show here to the left, they measure some sort of integrated contribution, including effects from larger distances and larger masses. And so they extrapolate down to short distance, but there are models in which their results don't really apply. So again, be nice to do something which is intrinsically small. In recent times, there's been actually an experiment done by a group of Aaron Kapitulnik here at Stanford, also unrelated to us, but where they use essentially micro cantilevers on which they glue a little test mass, and then they scan them and then they essentially look at the motion of the cantilever as they scan some sort of attractor pattern under it. So this complies with what I said before. Everything is miniaturized, but it still uses a mechanical spring, and which you'll see with our technique we avoid. All right, that's actually the current state of the art. So I'm essentially now taking things below a millimeter in lambda and showing you what is alpha, the limit in alpha. And you see that the limit in alpha is many, many times gravity. Those are, large numbers. And those are the different experiments that have been published over the last, 10, 15 years in this regime. If you go to even shorter distance, by the way, since Yuri is here, I can't resist not showing some neutron stuff. And here to the right, you see, if you go to even smaller distances, you really need something which has a charge radius smaller than regular matter. And the only thing we know that has that property is neutrons. And so you can do neutron scattering experiments. And those are essentially the way we actually extract results. But now you see that this alpha, instead of being 10 to the 4 or 10 to the 10, is now 10 to the 20. So those are even less sensitive, of course, and that's because simply neutrons zip around and there's no bound state of neutrons or things of this sort. All right, so there's lots of phase space to explore new physics. And so now let's see what kind of sensitivity we need first. And since this experiment, it's a small experiment, doesn't have a name, but my daughter many years ago now created a mascot that is this seal that is actually bouncing a ball on his nose, and so that's kind of, a seal is probably about 100 kilograms. A bathroom scale is a sensitivity of about a Newton. And then if you go down in the scale, a dust mite, one of those horrible things that are on your pillow probably, is about 10 to the minus 7 Newton in terms of mass, or of force in the gravitational field of Earth. An E. coli bacterium is like 10 to the minus 4 Newton. Our favorite virus here is about 10 to the minus 19 Newton. And then finally, a carbon atom is 10 to the minus 25 Newton. Atomic force microscopes measure small forces. The one you buy for a few tens of thousands of dollars, but is commercial, is 10 to the minus 12 Newton sensitivity. Very fancy cryogenic AFM is more like 10 to the minus 16 Newton per square root of Hertz. That's the kind of noise floor they have. Well, you'll see that we actually do better than that. But that's sort of to put things a little bit in perspective. Okay, so what about the technique? Well, the technique is actually the original technique is very is quite old, not as old as Cavendish's experiment, but it's quite old, and it goes back to Arthur Ashkin and collaborator, who in the 70s started levitating dielectric spheres into a laser beam that is propagating sort of upward. And you can see the scheme here, and Art actually got the Nobel Prize for this 2 years ago. So eventually this was sort of recognized as a very important contribution. And to the right, there is a picture. I believe the thing here in the middle is the microsphere. I also have to say that these people didn't know how to take photographs, because this is really hard to disentangle. Or maybe physical reviews didn't know how to, or applied physics letters didn't know how to print photographs. Maybe that's more the reason here, the problem here. In any case, that's sort of the original technique. And so over the last 40 years, the technique has matured a lot, and usually it's called, as a name, is called optical tweezers, and it's mostly used in a water suspension to study biophysics. And what you do is that you very carefully glue, so to speak, a little polystyrene sphere at the end of a polymer molecule, oftentimes a DNA molecule or RNA molecule, whatever. And then in your water, you focus a laser beam on that little microsphere, and you use the tweezer, that is the fact that now you grab that microsphere to pull that molecule around, and you can study all sorts of interesting behaviors of that long molecule this way. Now, in fact, as Art Ashkin had done a long time ago, we went back to doing this in vacuum. Actually, are to do this in air, but I mean, in a low density sort of environment, and we do it actually in high vacuum. And once you do that, now you use your, essentially, you can actually stare at this picture to the right a little bit and see what, how this thing works. But if you think at the microsphere as a little lens, you see that your focused light beam gets deflected by the lens when the microsphere is not exactly aligned. And the deflection, there is a momentum that the photons, when you deflect the photons, there is a recoiling momentum. And if you look at this long enough, you convince yourself that being centered on the beam is the stable equilibrium point. And as you shift to the left or to the right, you get a restoring force that pushes the microsphere back to the center. So that's the basis of your the optical tweezers kind of thing. Now, if you are in vacuum or in air, in addition, you shoot the laser beam from the bottom, and you use radiation pressure to also suspend the microsphere against the gravitational field of Earth, which in this moment, has nothing to do with the gravity we're measuring. It's just a nuisance. You have to support the microsphere somehow, and so you use radiation pressure also for that. And this is a number of advantages. As I just mentioned, the spring, there's no spring, or at least the spring is optical. And that means that you can use all sorts of tricks that have been developed for quantum optics to actually manipulate your sphere. So once you put it in this trap, there's lots of things you can do. Also, compared to a regular spring, this is almost isotropic along the 3 degrees of freedom, with the fact that the vertical degree of freedom, you have to do whatever it takes to counter gravity, and the other 2 degrees of freedom, you can do whatever you like. But that means that you can really study the motion and measure forces in 3 dimensions simultaneously, which we use in some sense, and hopefully later we'll use much more. And you can actually have very small dissipation. The trap is very, it's a very well, it's a very good conservative trap. You can get very high Qs. You can actually apply feedback and cool down the motion of the microsphere to very low effective temperatures. The microsphere is very well isolated from the environment. And so we essentially have, microsphere sitting there at microkelvin temperature in a totally room temperature setup. So we'll see much more of this, okay? But generally, the thing is that once you learn how to do this, you are opening an entire new domain of techniques and tricks that you can actually use for this. Okay, so that's actually the way one of our traps looks like. We have actually several, and I'll be showing you data from more than one trap. So I'm just showing you one of them. They're all similar. This is the fancy one. The others are somewhat less fancy, but they also came earlier. So we have more data from the others. But what you can see here, and maybe, there are the nice pictures on top, but the maybe more interesting part is at the bottom. This is a simplified optical schematics of this. And you have essentially a region where you have actually a pretty fancy laser that produces a beam that gets manipulated in such a way that eventually you can steer it to go inside the vacuum chamber and then propagate up, up respect to gravity, and be focused in a place where where you put your microsphere, and then the beam coming out of it contains the information of where the microsphere is, and so now you need to play some tricks to actually measure where the microsphere is, and you actually measure those kind of positions with resolutions which are of the order of picometers or something of this respect, of this kind. Of course, you have to integrate to actually go down to those kind of sensitivity, but you can actually see remarkably small position changes. The way this is done in our trap, and I think our trap is still sort of unique in this respect, is all the readout is interferometric, which for the horizontal degrees of freedom doesn't mean that much, but for the vertical degree of freedom is actually quite cute. The microsphere always reflects a little bit of light back, And so now you recombine that light that comes back with the reference wavefront from the same laser. And so now you just count, as the microsphere moves up and down, you see interference fringes, and you can essentially measure the height of the microsphere incidentally in absolute terms, because now you're measuring it in units of wavelength, and you know the wavelength really well. And so you can measure the height of the microsphere by just counting interference fringes. So all the feedback, for instance, the feedback on the degree of freedom, the vertical degree of freedom is done by essentially putting a servo, putting that vertical, that interferometry information in a feedback system. This is all possible by the fact that modern lasers, for $20,000, you can buy a laser that has a spatial coherence of like 10 kilometers or something. And so, exactly, after you do this reflection, you come back, the reference wavefront is just right compared to, on the distances we're talking about here. It's stable and it's perfect, and so on. There's all sorts of other gadgets here that I'll, in some cases, I'll cover as we go along. The other thing, the horizontal degrees of freedom are read out by essentially seeing the shadow of the microsphere in a quadrant photodiode. In fact, this is done again by recombining it with the reference wavefront, which helps a little bit with the background, but this is kind of a detail. The trapping light is linearly polarized, and the microsphere is always slightly birefringent. And so if you actually look at the wrong polarization state, which is done by this thing called PD3, photodiode 3, you are also measuring whether the microsphere is spinning, or you're measuring the angle of the microsphere respect to the apparatus, essentially. And so we'll use this later on as we go. Okay, so that's everything is very massive. It's built on a block of granite and so on to be stable. Okay, so the first thing, which is really a technicality, but how you actually put a microsphere in the trap. Those microspheres have diameters of about 5 microns. In fact, between 5 and 10 microns, depending on which experiment I'm going to show you data of, but call it, think about it as 5 microns. So they're really small. You can see them under a good microscope, and you can buy those things. The ones we use are made out of silica, or a particular type of silica, and you can buy them because biologists love them because they stick them at the end of DNA molecules and use them to drug the molecules. To actually use them in vacuum is substantially more complicated than in a water suspension, and you essentially have to vibrate with a piezoelectric transducer some quartz cantilever on which you have put some of the microspheres, and then they fall down, and if you're lucky, one of that is captured, and then you start playing with it. The first thing you can do, so after you've loaded your trap, as you can imagine, the microsphere will have some crazy amount of charge on it, just because it's kind of a random process, who knows. But it turns out that you can essentially change the charge state of the microsphere as you wish by shining UV light near the microsphere. And depending on whether you shine the UV light directly on the microsphere or on some surface next to the microsphere, you can essentially remove electrons or add electrons to the microsphere. And so you can actually see here, so typically when you start, a microsphere has maybe 100 electron charge on it. And you have to ask my students whether it's usually positive or negative. I never remember actually. You get both, but depending how you load, you get more one sign charge or the other sign charge. But that's not a big deal. You just start flashing your UV light and you bring it down. You can see here on the left, this plot, to 2 elementary charges, and then you do a little bit more, you get 1 elementary charge. Note how clear the charge quantization here is. This is like a fantastic Millikan experiment. This is 1 charge, and this is 0 charges. Keep going at 0, and I'll tell you more about this. And then if you shine more UV light, now it starts charging in the other direction, again by exactly 1 charge at a time. The way you measure how many charges there are is that if you recall, there's all this fancy looking gold-plated system around it. And in particular, the microsphere is surrounded by 6 electrodes, like in a cube, and you can bias any face of any of those 6 plates as you like differently. And so the way you measure the charge is essentially to apply some known AC potential between opposite plates, as shown to the top right, and then you see the microsphere move. And since you can measure, as I said, picometers position change, you are extremely sensitive. So actually, the way this measurement is done here is that we have some amplitude of voltage applied, of AC applied to those plates, until you are down at 0. And when you're at 0, you now apply 500 volts. You really ramp up your voltage amplitude. And so now you get very sensitive to whether there is some spurious charge on this thing, which is not quantized, maybe, or a smaller quantum of charge. And so by doing this, that's actually what happens in the blown up sort of plot here. You can check how close to absolute 0 the charge of those things is. And it turns out that you have a sensitivity of few 10 to the minus 5 electrons if you integrate long enough. And in fact, let's just not worry about, since I'm late, not worry much about the plot to the top right, but essentially we have the best limit. So actually, this is the kind of thing you do when you look for fractional charges, except standard experiments for fractional charges, and there's 2 of them here in those vertical bands. They look at lots of matter, so they have they can find charge 1/3 particles, even if they're very rare. And that's why this abundance vertical scale goes down, straight down in those previous plots. On the other hand, they don't have very good, they were looking for 1/3 of a charge. And so they don't have very good sensitivity in terms of fractional charge. Those are experiments, by the way, with magnetic levitation. This is Marinelli et al. And Kim et al. Is actually Marty Pearl, and is the experiment looking with essentially inkjet printer technology. It's a millican experiment looking for fractional charges. The other plots, the brown region, is actually coming from my group. That's the first measurement we did now a number of years ago. And then one of my postdocs has his own group now at Yale doing similar things. And so the blue part is actually Dave beating our old experiment by a couple of orders of magnitude in a newer measurement. And you can see that we go down to a fraction of 10 to the minus 5, sorry, to a few fraction of 10 to the minus 4 of an electron charge. And Dave used larger microspheres, so he actually looks at smaller abundances. Eventually, this will be the current limit on how close the proton, the electron charges are. So that's called neutrality of matter. It's a similar thing at this, but requires larger spheres. And so we'll eventually get there. Probably soon, either Dave or us will get there. Okay, so I told you that those things have that once you trap the microsphere, you get very small noise. This is the acceleration noise. You can interpret the noise as force noise or acceleration noise. In terms of acceleration noise, we have the best system on Earth, as far as I know. And you can see the parameters here. Now, of course, this is only true at certain frequencies. And so you can see here 43 degrees of freedom, X, Y, and Z, the power spectrum at different, for different frequencies. The red curve is done at, about a millibar or a torr, which is the pressure at which you trap the microsphere. And then you pump the air out. So at that high pressure, relatively high pressure, the microsphere is very well behaved because essentially the gas viscosity makes the trap very, adds dissipation and makes it very stable. On the other hand, for the same reason, the dissipation means that there's noise, and that's essentially Brownian motion. And so when you pump the air out, it becomes harder to keep you need feedback, active feedback, to actually keep the microsphere trapped. But on the other hand, you get much lower noise because the Brownian motion goes away to a large extent. So let me go a little bit fast here. So now, okay, so you can So how you do measurement of gravity or other similar measurements? Well, you bring a cantilever nearby, which may have different properties, and then you actually see how much you influence the motion on the microsphere with this cantilever. You can also see, by the way, the 6 electrodes. Those are those things that look like pyramids, and then the little facets with the holes are the real electrodes or the things that the microsphere sees. And then you use those holes to, first of all, to bring the laser in and out, but also to bring in various gadgets next to the microsphere. All right, so let me go fast here. Okay, so first of all, you can actually demonstrate the force sensitivity of the system. And this thing is actually one thing that is kind of difficult to see or to explain really well. So this device can measure a vector field, that is a force field, in 3 dimensions, in full 3 dimensions. And I cannot make a plot, a full 3-dimensional plot. So this is actually what I'm showing here. I'm showing a cross-section, which is XZ in this particular case. And then the little arrows are the forces along X and Z, but at different sites, X and Z. And so in this case, there is just a neutral, or at least a silicon beam, which is, the microsphere doesn't have charge, and there is a silicon beam sitting next to it at this kind of distance, which is about 15 microns. And you see that the noise here is of the order of, 10 attonewtons. It's a little bit worse in one degree of freedom than the other. This is also kind of old data, but 10 attonewton. This is 10 to the minus 17 Newton. So those are really, really small forces. Okay, the system is also linear, and this is actually, that was noise. Now, do you see a signal if you actually have something? And the answer is yes. You can put one charge on your microsphere because you can dose the charge as well as you like, and now you can actually bias that silicon beam, which is also gold-plated, and now you actually map the electric field. It's like you're mapping the electric field. And again, full vector. So you get 3-dimensional readout in a 3-dimensional volume of space, and the volume of space is something like few hundred micron by few hundred micron by few hundred micron. Okay, so this is actually, so this is like essentially it's like an atomic force microscope with some important differences. AFM reaches smaller distances, so they're better at that. But we have full 3-dimensional readout that they usually don't have. So it's kind of a complementary tool to atomic force microscope. You can also, and it's important for what comes later, measure the mass of those microspheres actually really surprisingly well. And this was invented by one of the graduate students, by the way. So the thing is that, in principle, you can weigh the microsphere by measuring how much, laser power you have to shoot up to keep it in equilibrium, to keep it balanced, to balance the force of gravity. But this is really not very practical because you see, who knows exactly how much you need to measure the integral between the power profile or of the laser beam and the microsphere. I don't know how to do that. However, what you can do is that you can attenuate your light, and you measure how much light you're transmitting through there because you have a photodiode, which is very linear and very well behaved. And so as you change the amount of light that goes through, you have to, you see how the microsphere, essentially, effectively, how the microsphere is moving. And so by doing that, you can then, that's what you can see to the right here in the plot to the right. And so now you can extrapolate that thing to 0 optical power. And that gives you that allows you to actually measure the force, what kind of force you need to sustain the microsphere up there. Sorry, actually, I should have said something else. You actually put, again, one charge on the microsphere, and now you essentially change the intensity of the laser beam and balance that with electrostatic force from your electrodes. And so you extrapolate to 0 beam power, and by doing this, you actually measure the weight of the microsphere. And you can do it in many conditions and so on. It's all rather, really quite consistent. And so you get this kind of thing, which for those microspheres, those are those 4.8 micron diameter microspheres, the mass is about 80 picograms. Notice those last 3 points here. Those are just normal microspheres that are measured, except the student is really clever, and after measuring the microsphere, is able to put it on a silicon plate. That is, you can see here, 1, 2, 3. Those are the 3 microspheres that were measured last. And so once you have them on the silicon plate, you can actually then take it out, put it in an electron microscope, and measure the diameter of the microsphere very well, which was done. And when you do that, you actually end up also with the density of the microsphere. And the density of microsphere is 1.55 gram per cubic centimeter with a rather small uncertainty, which is actually lower than the fused silica density. And this has to do with how they make them. Those are commercial microspheres. We just buy them, but apparently there's some porosity in those things. Next, you can actually try to spin the microsphere. This has been done in various ways by others, but the way we do it is a bit different. That is, I told you that the microsphere has a little bit of an electric dipole moment and is also slightly birefringent. And so now, when the microsphere spins, you can actually, by looking at the polarization that emerges, you can actually measure the orientation of the microsphere, and so you can actually measure its rotation. Since there is an electric dipole moment also, you can use the electrodes that I have and essentially build like an electrostatic motor that spins the microsphere that way. And so that's actually what you can see in the animation. The animation essentially shows the direction of the electric field in the middle of the trap as it's seen by the microsphere. And so the electric dipole moment stays aligned with that thing and it gets dragged around. So if you think about it for the next slide, there is an instantaneous direction of the electric field, and then there is the instantaneous direction of the dipole moment, and there is an angle phi between the two of them. All right, so that's actually what you see here. You can see that you get essentially a big line in the spectrum of the light on the polarized on the wrong polarization of the photodiode. The photodiode reading out the opposite polarization to that of the trapping beam, and this thing goes around at twice the frequency of the rotation of the microsphere. You also see some side bands, and I have one of them kind of blown up down here, which are in this case about 1600 hertz. Actually, no, this is radians per second. Anyway, whatever. At some frequency respect to that center peak. Now that is the libration of the microsphere. So if you think about it, if you put yourself in the reference frame of the electric field, the dipole moment is essentially wiggling around the direction of the electric field. And so it's essentially is libration, like in astronomy, you'd call that libration. So, okay, good. So we'll use this in a minute, but in the meantime, if you spin the thing up with my electrostatic motor and then you let go, the thing slowly, you start from 100 kilohertz or something, and then this thing slows down, and it slows down exponentially as you expect. There is actually people working for LISA, for the gravitational wave observatory in space, have done lots of gas dynamics calculations that can be reinterpreted to actually to measure, to predict the drag from the gas. And so the model fits very well, as you would expect. And so that's actually, so we'll see in a minute, we can actually turn it around and use that to measure the pressure in the vacuum chamber. But the libration frequency, turns out, can be written as the formula up here, and it depends on the electric field, which is known, times the dipole moment over the moment of inertia of the microsphere. So if I, and as I change the strength of the electric field, the amplitude of the electric field, of course, it wiggles at higher and higher frequency, as you can imagine. And so you can use this thing. You see, it fits very well, again, this simple model. I mean, the model is kind of trivial, but it fits it very well. And so you can use this to assume that the density, the moment of inertia, you assume that the density is uniform from the previous measurement. And so you can calculate the moment of inertia. And then from that, you can extract the dipole moment, which is about 100 electron micron. Of course, this depends on the specific microsphere, but it's always, between 50 and 200 or 300 electron microns. That seems to be a property of this material. So, you can also measure the pressure, if you want, or the drag by essentially by seeing at what pressure the microsphere unlocks from this arrangement. So imagine now I'm essentially spinning the microsphere and keep it spinning it, and there's going to be some delay between the orientation of the electric dipole and the orientation of the electric field instantaneously, and that is because the drag means that you need to pull with some, you need some torque in order for this thing to follow you. And so now, as you increase the pressure, which you can see here on the horizontal axis in those three plots to the top, you see that angle between the electric field and the dipole moment increases, and eventually get to the point where the angle becomes random, because now you have unlocked. That is, in other words, you went all the way to pi over 2 to 90 degrees. That angle is 90 degrees. And now you are kind of, if you go beyond that, you lose the microsphere, you lose the rotation lock. And so you can use this to actually measure the pressure. And in fact, this is something which is, it's an absolute measurement. You can use that Italian paper I mentioned before, the LISA paper, to actually to calculate in absolute, without any calibration constant, your pressure in the system. I need to actually go fast, and this works for many different species. Here I'm trying different gases, and this also works very well. So okay, so the thing also works as a gyroscope, but since I'm running out of time, I will skip this and talk about the final thing, that is the gravity. So I need like 10 minutes for this. So okay, so now if you want to study gravity at short distance, you make yourself an attractor that looks like the thing to the right. It's microfabricated on a silicon slab. The silicon slab is about 10 microns thick, and alternates silicon and gold, as I call them, fingers. You can think of it as a piano keyboard where every other key is a different density. And then, of course, you want to make this thing as equipotential as possible, so you coat everything with gold. The fingers are about 25 microns wide, and the gold you put on top is much less than 1 micron. So it doesn't really change much the gravitational structure of things. In addition, we also have what we call a shield. That is this thing that looks yellow, bright yellow here. And that is something, looks exactly like this. Is also microfabricated with silicon, is intrinsically three-dimensional sort of, and it's got that sort of edge that is protecting the microsphere from the moving potential electric, from the electric field that the attractor may produce as it's moved. The shield doesn't move, so even if it produces some electric field, it doesn't really matter, at least at first order, because it doesn't really move. Now, I should add that the thing is that even if you coat everything with gold, metallic surfaces are never perfectly equipotential. There are patches of charge. Essentially, the crystal structure means that the work function is slightly different places. And so on the scale of 10 to 100 microns, there are those patches of potential, which can be like 50 millivolt strength, sort of something like this. So it's important to have this kind of shield. The separation between the attractor, that is the pattern kind of element, and the microsphere was shown here, which is, call it 15 micron in X and Z. And we scan the attractor along Y. And for the first measurement, for various reasons, which if I have time, I'll tell you later, we only look for the time being at the Z response, or at least the measurement is done looking at the Z response, the vertical response of the microsphere. And of course, now you can use, essentially look at the, use essentially a simulation or a calculation to see what kind of pattern of frequencies you expect. And then you essentially make a filter that looks at those frequencies. This is the way the attractor looks like. It's just kind of fun to see, but the information was in the previous slide. And this is the shield. And you see that that's exactly the way I described it. It's just that it's like a canyon I just showed you the previous slide, half of it, because that's the only thing that's really relevant. Okay, this is actually the way this thing looks like when it's going. The image is somewhat aberrated because it's done through a microscope that looks through our trapping mirrors, which are parabolic mirrors, which works best for the trap, but doesn't give very good image quality at the end. Okay, then this is just to show you that the thing is really moving back and forth. Actually, you do the measurement at 13 Hertz, so this is slowed down so that we can actually see it. This is, okay, so now the two continuous histograms are red and black, are the essentially the noise spectrum, the spectral density of the noise at different frequencies, with the attractor that doesn't move, that's black, and with the attractor that moves, which is red. And you can see that there are spikes, but most of the spikes, or many of the spikes, actually exist both without moving and with moving. So clearly that is not signal, that is just the noise of the system, essentially. You can also see that the noise doesn't get much worse when you move the attractor. That's good news. The blue little sort of I don't know, plateaus, this is where the pattern you expect for the signal with the parameters of the experiment and alpha, that is the strength of the Yukawa term, 10 to the 10, which is kind of large, but that's just to show you what it looks like. And so then essentially what you do is that you do a statistical analysis and you see how compatible your data is with the blue, with that pattern done in blue. Okay, so as I said, for the first measurement, for reasons that have to do with the background, the Z channel, that is the vertical degree of freedom, works much better. And so adding the other 2 degrees of freedom doesn't change the sensitivity. So we're just using Z for the time being. And we use not really all of those frequencies, but a subset. There's some of those frequencies, there's more sensitivity. And so to keep things simple in the fit, we only use a subset of those. And so we use 6 harmonics. And when you do that, then you do a statistical analysis and you pull out your signal. To the right here, what I'm showing is for the 6 harmonics that we care about, over the measurement length, which is about a day, about a little bit more than 24 hours of measurement, how those frequencies, or the strength of those frequencies, changes with time. And you can see that there is some change in time. Which of course cannot be gravity, because gravity is not supposed to change in time. So there's some background that changes in time. And when you do your fit, of course, you can at least take advantage of that. That is, in other words, you can essentially say, well, my signal should not be changing in time. This is equivalent to essentially projecting everything on the vertical scale, which is what's done in this kind of, and averaging, taking the central value of this thing, of each frequency, and projecting it to the right. That is those 6 points that I'm showing here. Then you do some sort of systematic study and you estimate your uncertainties, which is shown here. But let's go quickly on this. And then, but you see that there is a finite effect, right? When you see here, clearly, most of those points are a little bit above 0. So there seems to be a little bit of a, I never remember whether this is attractive or repulsive, but there is a little bit of a force, residual force that you're having there. And this goes back to what I said at the beginning, that electromagnetic backgrounds, or backgrounds in general, are important. So this measurement is not statistics dominated, is systematics dominated. And as a test, we've said, okay, well, what if there is some residual electromagnetic interaction? And it turns out that, remember I told you that there are patches of charge, or there can be patches of charge. The shield shields those really well. But one thing we discovered later, of course, after we've done the experiment, that is not shielded particularly well, is the contact potential. So if the shield and the attractor are slightly, they're both connected to the same together electrically, but there are contact potentials in general. And if there is a 50 millivolt potential difference between the two of them, then the leaking electric field applied to 1,000 electron microns. Remember, I told you that the electric dipole moment is more like 100, 200, or something like this. But this is not. This is the right order of magnitude. then it gives you an effect that is similar to the one we see, to the background we see, or to the, call it signal, or to whatever we see. So there's other backgrounds that we've discovered in the meantime. One is stray light, which it's a long story, but it's kind of technical and maybe it's not essential here. And there is also vibration. Smaller effects are laser pointing noise and Casimir forces, which for the time being are not expected to be really dominant. All right, so if I put all this together and I play very conservative, that is, I say, there is a background, I'm pretty sure it's a background, it's not a signal, but I will do an experiment without discovery potential. And essentially for the time being, this is the first measurement. Just don't, just assume that the limit is at the level of the background that I have in there. Then I get the profile you see here, which is not as good as the best measurements yet, but this is the first time that has been done with this technique. And also this technique is, I remind you that it's the only one where you can really, where you only, where you really, everything is the right scale for the measurement you're doing. So we are in the process, since we understand the backgrounds reasonably well now, we are in the process of actually fixing them and doing a number of upgrades to the system, which let me just show them all together here. The electric dipole moment background can be first fixed by understanding it better, but also you can essentially change the potential between the attractor and the shield and find the minimum of the effective interaction. And that is the one where the two have presumably the same potential. So that's something that can be done. We are substantially working on reducing scattered light. Yuri was very excited about my gold-plated things. I don't like them actually gold-plated now, and we're coating them all with black graphite. Looks less sexy, but hopefully works better. And then, there's other things which are more sophisticated, like instead of using a quadrant diode to read out the position, we've made a 100 pixel, 10 by 10 pixel photodiode that we'll use so that we have a rudimentary image. And our Swiss collaborators, now we have Swiss collaborators, and of course, being Swiss, they made a little clockwork kind of thing for us. That is, instead of an attractor that scans back and forth, that has more vibration, is a rotary attractor, so that hopefully will have less vibration. So this brings me to the conclusion. After 200 years of mechanical springs, I think we've made the first measurement of the 1/r² behavior at below 50 microns, which is done with only optical components. It took a few years to actually establish things, but in the process of doing that, we've also discovered all sorts of other things that can be done, from vacuum gauges to better navigation devices with gyroscopes and all this kind of stuff. The first measurement is now on the archive, resulting in a conservative limit, which is not as good as the other limits yet, but hopefully will be there soon. And let's see what else I told you. Yeah, and so with the upgrades we're doing now, I hope when we come back to life, probably in September, we will have a substantially better sensitivity. And this is actually part of the group that has done all of this, graduate students, postdocs, and even one undergraduate, some of which, actually two of which has already moved to other careers or other things. And we also, I should acknowledge, first of all, our funding sources, which are NSF, Office of Naval Research, and the Isaac-Simons Foundation. And also we have our friendly competitors at Yale, with which we compare notes regularly. And that's the group of Dave Moore down there. Thank you.
Thank you, Giorgio. That is extremely interesting and exciting. Please, any questions? Okay. Give people a second to formulate their questions. Any questions? Giorgio, it seems that you were so clear
Yeah, I was either completely unclear or totally unclear. I don't know, one of the two.
I think I'm unmuted. Can you hear me now? No.
Yes, please.
Okay. The question is, you mentioned that the very briefly that the Casimir force would be not important in these, but at these small distances, it seems like are you ruling this out based on calculations or on measurements?
No, that's based on calculation, and there are uncertainties on the magnitude of the Casimir force, which are, I would say, mostly technical. You know, you need to know the properties of the surface or electrical property of the metals and all that. So there are some uncertainties, but they become important at you know, a factor of a few at least, if not an order of magnitude smaller distances. So by the time we get to 1 micron, that will be really important, you know, really important. But at our distance of like 10 microns, which is the rough distance we have now, those are really small. And even with the uncertainties in the calculations, it's pretty clear that those are not the dominant kind of effect.
Thank you.
Okay, more questions? It is clear, Giorgio, that what you are doing, that it is very unfamiliar to us, and not many people are doing that. But I'm so happy to see that this is kind of approach which was used by people like Melike and Rutherford when you do everything in the next room to your office is alive, and you can do such experiments.
Yes, this is sort of the ultimate Millikan experiment. Yes.
Yeah, and it is not like most of DOE project where 1,000 people are working and they don't even know each other. I like this style and very much.
Yeah. We usually say that, you know, our management is such that we meet on Tuesday, decide during the meeting to change parameters of the experiment, and by Friday there's the data. We look at the data. Essentially, that's as much as.
Yeah, that's great. That's great. All right. Any other questions? I'm still recording. Unfortunately, I forgot to press the record button at the very beginning, and we'll hope that you can send your slides. I will
Sure.
also your slides. All right. If there is no much questions, then please let's thank Giorgio again and wish him success in his beautiful experiments.
Thank you all.
Thank you. Thank you. I
you.
enjoyed it.
Yeah.
Thank you.
Hello
Thank you,
to Dr.
Giorgio.
Compton
Bye.
also. Hello, Dr. Compton.
Hello.
Okay. Bye-bye.
Sorry.
Somebody
Okay.
I know, I don't know. Sorry.
Yeah, this was Eric Bermel. I was in your thermal physics class. I was just saying hello to you. Sorry.
Oh, congratulations. You made it through that course. You know, Bill Bugg once said that, or no, I guess it was Lee Riedinger said that when the department wanted to get rid of somebody in the department, they would make them teach thermodynamics. So I taught thermo for 5 years and they still didn't get rid of me. Good to talk to you.
All right.
Okay. Bye. Thank you,
Bye-bye.
Yuri. Bye.
Thank you, Joe.